Welcome everybody to this week's edition of HoloTube, today with Christiana Pantelidou, and she's going to talk about nonlinear response in real-time holography. As you can read from the slide, I'm very happy to see you again, and we're very happy to have you here. To take it away, the screen is yours.
Thank you very much. So let me start by thanking the organizers for putting together such a wonderful online seminar series, and also for giving me the opportunity to present some of my work to you here today. And in particular, in this talk, I'd like to tell you a little bit about some work that I've done recently in this paper here in collaboration with Benjamin Withers from the University of Southampton on the topic of nonlinear response in real-time holography. And let me jump right in. Okay. So in this talk, I'll be interested in the retarded response of strongly coupled holographic quantum field theories, and I'll be thinking in terms of finite temperature. Now, the most obvious and in fact the simplest observable within this class of observables is nothing but the retarded two-point function that we all know and love. So, for example, for say an operator calligraphic O, this retarded two-point function would look something like this. In particular, I denote this object as GRA, and the RA notation, if you're not familiar with it, I'll give some more details in a couple of slides. And this quantity here, as the name suggests, is a function of 2 points, x1 and x2. And these are precisely the locations where I do the operator insertions on in my quantum field theory. Okay. And in order to compute this quantity, I need to compute this right-hand side here. So if I just received the HoloTube email. If I have an operator at position x1 and an operator at position x2, then I take the commutator of the two. Then I compute the thermal expectation value, and then I multiply this whole thing by this theta function that you see here that essentially says that x1 should be in the future of x2. Okay, so from this definition, it's not too difficult to see where this function has support. Okay, and in particular, this is non-zero when x1, when point x1 lies in the future light cone of point x2. So if the two were space-like separated, then this commutator would have been 0. And if x1 was in the past of x2, this theta function would have been 0. So this retarded two-point function is non-trivial only when x1 is at the future light cone of point x2. Now, just simply from this statement, it should be clear that the retarded two-point function has a crucial dependence on the time ordering of the 2 points x1 and x2. And it's precisely because of this reason that it poses a little bit of a challenge to the standard holographic approach. And strictly speaking, in order to compute it, one is to go into the realm of real-time holography. And since this point is very important for what I have to say today, let me elaborate a little bit further. So according to the standard ADS-CFT, or the standard holographic prescription that we all know, in order the partition function of the quantum field theory that I denote here by ZQFT is equivalent to the gravitational path integral, which we approximate by evaluating it on a saddle point. Okay, and this is what I denote here in the right-hand side. So this is the statement of standard holography, and it actually goes a little bit further from what I just said in words. And this is to say, if we have a source J in our quantum field theory, on the gravity side of the duality, this source becomes boundary conditions that one needs to impose in the UV part of our geometry. Now, this statement here makes no statement whatsoever about the initial state of the state of the quantum field theory, or equivalently, it makes no statement, no reference to the initial data that one needs to consider for the bulk fields on the gravity side. And as such, it's very well suited for computing Euclidean quantities, but it's not suited for computing things that have an intrinsic time dependence, like, for example, the retarded two-point function that we were discussing earlier. And just to drive the message home a little bit further, say we want to compute the simplest thing, so the retarded two-point function of a scalar operator. Then on the gravity side of the duality, we simply consider a standard scalar field. And since we're still in linear response, the only thing we need to do is to solve the Klein-Gordon equation for that field. And we need to solve that equation subject to boundary conditions. We know what those are. They are prescribed by the boundary sources in the quantum field theory. But we don't know what initial conditions to consider for this scalar field. Okay, so the punchline is that just simply from this statement here, we cannot compute the observables of interest. This is just not enough. We need something on top of this. Now, you might be a little puzzled by this statement because such two-point functions have been extensively studied in the literature. So how does that compare with what I just told you? And it turns out that people have been extremely clever, and they came up with a prescription that allows us, not only allows us to compute these retarded two-point functions, but it also gives the right result, obviously. And those people, those very clever people, were Sohn and Starnets and Herzog and Sohn in these two papers. And essentially what they proposed is that on top, going in the wrong direction, that on top of this standard holographic statement, we also need to impose ingoing boundary conditions at the horizon of the black hole that says the temperature of the quantum field theory that we're interested in. And not only this very clever prescription gave rise to the correct results, but it also gave rise to very beautiful and very universal result that relates poles of these correlation functions with Quasinoma frequencies of the black holes that we have in the bulk. So we have a universal behavior between black hole written down in the form of Quasinoma modes, and in this case, linear respond correlation functions. But even though this prescription, it works and it gives nice results, it's a little bit unsatisfactory. And the reason is that we're doing essentially a mixture of things. We are imposing boundary conditions in the UV of our bulk geometry, and those for those we have a clear interpretation from the perspective of the quantum field theory. But on the other hand, we are also imposing something at the black hole horizon, and we do not have a good interpretation of those boundary conditions from the perspective of the quantum field theory. And for this reason, a more satisfactory way to go about doing this calculation is to start from scratch from real-time holography, like, for example, the prescription of Skenderis-van Rees, and do the computation there. Now, one can actually prove that starting from there, from real-time holography a la Skenderis-van Rees, they can explicitly derive this ingoing boundary prescription that Sohn and Starnets and Herzog and Sohn gave us a long time ago. Okay, and I'll show this later on in this talk. But as I said, even in the title of this talk, today I want to go a step further from linear response. I want to go to the nonlinear level. And the most natural and the simplest thing to compute is the retarded three-point functions. Now, a retarded three-point function looks something like what you see here. In particular, I denote this quantity by GRAA, and now it's a function of 3 points, x1, x2, and x3. In order to compute it, we need to evaluate these two terms, this one and this one. Let me start first by discussing the first term. So in order to compute this, we need to take the commutator of the operator we have at position x1 with the operator at position x2. And then we take the nested commutator of that with the operator at position x3. Then we take the thermal expectation value. And now we multiply this whole lot with two theta functions that essentially say that x1 is in the future of x2 and x2 is in the future of x3. So this is the first term. And then we have another term that's essentially the same as the previous one, but now with positions x2 and x3 exchanged. And just like what we did before for two-point functions, let's discuss where this retarded three-point function has support. And it's not too difficult to see that this first term is non-zero when x1 lies in the future light cone of point x2 and x2 is in the future light cone of point x3. And similarly, the second term is non-zero when x1 is in the future light cone of now point x3 and x3 is in the future light cone of point x2. So the order of x2 and x3 does not matter as long as x1 is in the future light cone of both of them. And now we want to compute this retarded three-point function using holography. So what we need to do is we need to solve a nonlinear problem in the bulk. And in order to actually do this computation, we need to specify what sort of interaction terms we consider for our fields on the gravity side of the duality. And to be very specific, in this talk today, I will be computing the retarded three-point function of a scalar operator. So on the gravity side, I'll be considering a scalar field. And the interaction term that I will be considering for that scalar field is the simplest possible. It will be a lambda phi to the cube interaction term. In order to do this computation, I will be starting from scratch. I will be taking the real-time holography prescription of Skenderis-van Rees. And in particular, I will be making no assumption about ingoing boundary conditions at the horizon. Okay. So this is what's on the menu. Let me give you a few motivations for doing this calculation. Now, the first motivation is the following. So I think it's clear to everyone in this audience that ADS-CFT or holography is an extremely powerful tool for studying strongly coupled quantum field theories in real time. Now, this real-time aspect of holography hasn't been explored to its full extent as of yet. And in this project, we're sort of trying to push the real-time holography framework a little bit further. That's the first motivation. The second motivation is we want to understand whether the simple ingoing prescription that Son and Starnet gave us for two-point functions, whether we can also use it when we're computing higher point functions. And as we'll see later on in the talk, the answer to this question is yes. Now, a third motivation is we want to see whether the universality that Son and Starnet found at the level of two-point functions relating black hole ring down with linear response functions, whether that can be taken to the nonlinear level. And the answer to this question is that at least at the level of three-point function, this will go through. Okay, so these are three motivations, but talking more broadly, this computation lies in the research line that makes an attempt to understand nonlinearities in black hole spacetimes with both ADS and also flat space-time boundary conditions and their implications for various observables. And I don't have much to say, especially about flat space-time at this stage, but I can elaborate a little bit further if there are questions at the very end. And with this, I finish my introduction. Are there any questions before I go on? Okay, I'll take the silence as no questions. So before I move on to the bulk of the calculation, I'd like to give a short overview, really short overview of what real-time holography is, just to make sure that everyone is on the same page. So as I said several times already, today we want to compute retarded three-point functions. And in particular, we want to more generically speaking, we want to compute nonlinear correlation functions. And the most natural way to do that is by constructing a generating function, or better, a generating functional for the quantum field theory that we're interested in. So we are at finite temperature, remember that. In such a way that when we take derivatives of this generating functional with respect to the sources of the quantum field theory, we will recover the correlation functions of interest. Okay. Now, for the computation we want to do, we need to consider our quantum field theory living on this closed Swinger, the so-called closed Swinger-Keltish contour, which is a complex time contour. So we are not considering a quantum field theory in Lorentzian time. We are not considering a quantum field theory in Euclidean time. Instead, we are considering a quantum field theory that lives on this complex time contour. Okay, and let me describe this contour in a little bit more detail for you. In particular, it has three segments, as you see here on this image. In particular, it has two Lorentzian segments and one Euclidean. So segment 1 is this blue segment. It's parameterized by Lorentzian time t1 that flows from 0 to some final time tf. Then we have another Lorentzian segment parameterized by time t2 that flows in the opposite direction, so from t final all the way down to 0. And then, last but not least, we have a third segment, this red one here, which is a Euclidean segment parameterized by time tau. Now, these two dots here, they indicate that those 2 points are identified. So in fact, we don't have a Euclidean segment, we have a Euclidean circle. And the period of this circle is given by beta, which is inversely proportional to the temperature of the quantum field theory that we are considering. And it's not too difficult to see what this Euclidean circle does for us. Essentially what it does, it prepares the state of the quantum field theory. And the easiest way to see this is, say we wanted to do a time evolution along this Euclidean part of the contour. Then what we would have to do is we would have had to insert e to the minus beta h, but this it's easy to recognize as the density matrix of the quantum field theory. Okay, so this Euclidean circle here simply prepares the state of the quantum field theory that we're looking at. Now, a little bit of notation. So in what follows, I will be inserting a source J1 associated with operator 1 on segment 1, okay? And I will be inserting source J2 associated with operator O2 on segment 2. And I will have no sources on the Euclidean segment, okay? Now, it turns out that it's convenient to do a little change of basis, and instead of considering O1 and O2, or equivalently J1 and J2, to go to the AR basis, where, for example, we consider JA and JR. JA is now the difference between the two sources that we have on segment 1 and segment 2, and JR is the average of the two sources. And similarly, for the operators themselves, we have OA and OR, the difference and the average respectively. Now, with this notation at hand, we can write down the generating functional that we wanted for our quantum field theory that now depends on the sources JA and JR, and it takes this form here. So the sources and the operators appear in this exponent in this particular way, and TP here is the contour ordering operator. Okay, so if I vary this generating function with respect to the sources JA and JR in this particular way, I get the corresponding correlation function. In particular, if I vary n times, I get the endpoint correlation function. And just as an example, let's look at two-point functions. So if I vary this generating function with respect to JA twice, what I get is this symmetric two-point function GRR, which is not too difficult to show that it depends on the anticommutator of O1 and O2. If instead I vary this generating function with respect to JR twice, what I get is GAA, and it turns out that this is trivially 0. And then if I vary it twice, once with respect to JR and once with respect to JA, depending on the ordering, I get either the retarded two-point function GRA or the advanced two-point function GAR, both of which are both of which depend on the commutator of operator O1 and O2, and they are in fact related to each other with time reversal. So we see that within this framework, we don't only get the retarded two-point function, but we actually get a 2x2 matrix of two-point functions. So we have 4 components. Now, if we take into account the fluctuation dissipation theorem, out of those 4 components, it turns out that just one is independent, and usually people take that one to be the retarded GRA. Now, we are interested in 3-point functions, so we want to vary this generating function with respect to sources 3 times. So what we'll get is a 3x3 matrix of correlation functions. So we have 9 components in total. Now, if we take into account the fluctuation dissipation theorem, it turns out that only 3 out of those 9 are independent. And usually people take those to be GRAA, GARA, and GAAR. Okay, so out of those 3, today we'll compute just one, namely the retarded one, the GRAA. Okay, and we'll leave the other 2 for the future. And you see how one can get higher point functions by varying this generating function. Okay. So, and at this stage is where the power of holography kicks in, because it gives us a way to compute this, this generating function from the gravity side of the duality. But in order to do that, we, as I said on the very first slide today, we need to evaluate the path integral on a gravitational saddle. The gravitational saddle that is dual precisely with to the contour that we consider on the boundary. So this gives rise to the following question: what is the bulk geometry that is dual to this complex Swinger-Keltish contour? Okay, and this is precisely the question that Skenderis-van Rees in their paper in 2008 that they answered. Essentially, what they did was they said we fill in each of the Lorentzian segments by a segment of a Lorentzian black hole. Okay, so this is one Lorentzian black hole segment. This is another Lorentzian black hole segment, and we fill in the Euclidean circle with a Euclidean black hole, or if you want, a Euclidean cigar. Okay, and not just that, they also said that that one needs to demand that this piecewise geometry is smooth and it's C1 at the joints. Okay, so it's not these three pieces, this piecewise geometry need to obey some conditions on these dashed lines that indicate the matching points. And those conditions are precisely smoothness and C1. Okay. So for computations, according to the Skenderis-van Rees prescription in real-time holography, what we need to do, we need to consider, instead of the standard single black hole that we always consider, we need to consider this piecewise Bal geometry. Okay. And this is what we'll do in this talk today. Okay. Are there any questions before I move on?
Yes.
Yes.
Hi, Christiana.
Hello.
My question is, as you said, on this Schwinger-Keldysh contour, you should impose this fluctuation dissipation theorem in order to get some consistency in terms of equilibrium. But what about this formalism by on the gravity side? Should you impose any fluctuation dissipation theorem like thing, or the relation between GRA and GRR is already satisfied?
So I think the idea is that you don't impose anything. It should be, if you do the calculation correctly, it should be true.
Okay, then the next question is, how does this black hole realize this relation, this fluctuation dissipation theorem?
If you give me probably 10 slides time, I'll show you.
Okay, mathematically. Okay, thanks.
Yeah,
Sorry.
yeah, mathematically. So we'll see that precisely, just to give you the upshot, we'll see precisely that the fluctuation dissipation theorem at the level of 2-point functions is essentially embedded in the bulk-to-boundary propagators in this piecewise geometry that Skenderis-van Rees pushed forward.
I see.
But I'll show you the formulas in a little bit. Any other questions?
Christiana, one question. I'm not getting the picture. So do you change the background geometry to make this? Like, do you first consider some Euclidean solution, and then for the one that enters into the T1 and the T2 piece, the Lorentzian?
I'm not sure what you mean.
I'm not getting how you do this computation. So it seems in the red piece,
yes,
you don't have, like, the metric is positive definite.
It's a Euclidean metric, yes.
But then for the other part, you have it.
Yes, yes. So you have a mixed signature geometry. So
Okay.
if you want to do numerics, you do numerics on 3 segments, say M1, M2, and ME. And then you impose that on the joints, you have this condition here.
Okay.
You're understanding right. It's not a trivial computation to do.
Yeah. Okay, thank you.
Yeah.
There's another question. Is there a kind of group theoretical realization of this construction? For instance, like for BDZ black holes, you have this SL2Z constructions, factoring and coset spaces. Is there some kind of equivalent to such a construction when you have these 3 segments, a Euclidean one and 2 Lorentzian ones? Is there some equivalent? I'm just wondering.
I don't know. Maybe
okay.
there is. It's just I'm not aware of anything like that.
Oh, okay. Thank you.
Any other questions? Okay, I'll take the 5-second silence as no questions. So let me now move on to the main part of this talk. So as I said, plenty of times already, we want to compute the retarded 3-point function of a scalar operator So on the gravity side of the duality, and in particular on this piecewise geometry that I just showed, we are going to consider a massive scalar field. And we are going to take the interactions of this scalar field to be lambda phi to the cube. Okay. When we have no sources on the Swinger-Keltish contour, so on the boundary of this geometry, then our scalar field is trivial on all 3 segments of the geometry. Okay, and this corresponds to the expectation value of the operator OR to be trivial. Now, let me do the following. Let me turn on perturbative sources. Namely, I want to turn on a source J1 on segment 1, a source J2 on segment 2. I want to take the 2 to be equal to each other and equal to JR. And I want to take that JR to be perturbatively small. So epsilon will essentially be controlling that expansion. Okay. When I do that, essentially the existence of these perturbative sources will back react on my scalar field, which will now become non-trivial at order epsilon. And I denote that non-trivial behavior at order epsilon as psi. And then having non-trivial psi, precisely because of the interaction term, that will generate a non-trivial profile for my scalar field at order epsilon square, which I denote by chi, and et cetera, all the way to high orders. But for the purposes of this talk, I'll stop here. And as we'll see later on, psi essentially controls the 2-point function and chi controls the 3-point function. Now, this is for the scalar field. Of course, we also have the metric, so the geometry itself. And it turns out that up to order epsilon square, the geometry does not receive any corrections. Okay, so the geometry is simply given by this piecewise geometry that I introduced on the previous slide. Okay, now given that the geometry is piecewise, it makes sense to consider this psi and chi fields as being piecewise as well. So we have psi 1 on segment 1, psi 2 on segment 2, and psi e on segment on the Euclidean segment, and similarly for chi. Okay. Now we plug this ansatz into the equations of motion for the scalar field, and that equation reduces to 2 boundary value problems. So at order epsilon, we have to solve this equation for psi 1, psi 2, and psi e, subject to boundary conditions. And these boundary conditions are essentially that the scalar field psi 1 should have source J1, psi 2 has source J2, and the Euclidean scalar field psi has no source. So this is the first boundary value problem that we want to solve. And the second boundary value problem, which arises at order epsilon square, essentially has pretty much the same operator acting now on chi I, but now we have a source on the right-hand side that is essentially given by the field at order epsilon. Okay, and in this case, the boundary conditions are simpler in the sense that we impose that we have no sources for the scalar fields chi. Okay, this is because we want to measure the response of the system at the first nonlinear order given the sources at order epsilon. Okay, so the task for the remaining of the talk is essentially to solve these 2 boundary value problems, always imposing the matching conditions on the joints as prescribed to us by the Skenderis-van Rees real-time holography prescription. Okay, so this is what we have to do. And let me start by solving this first boundary value problem. So the approach that we will follow goes like this. We will start by assuming a single delta function source on segment M1. Segment M1 is the bulk infield of segment one of the Swinger Celtic contour. So strictly speaking, is this slice at the back here. Okay, and by having a delta function at that point, we will consider the influence of that delta function on all three pieces of our geometry. Okay, and we'll measure this influence by considering the bulk to boundary propagators. Then we'll put a delta function source on the boundary of segment M2, and once again compute the influence of that delta function on all three segments. And then if we have all those bulk to boundary propagators, we can simply convolve those with the sources in order to get the actual fields psi1, psi2, and psi-e on all three segments. Okay, so that's the plan. Let's see how we do that in more detail. So as I said, we start with a single delta function on M1, and we want to compute the bulk to boundary propagators. Okay, so we want to compute delta 1, 2, delta 2, 1, and delta E1. So the second index here indicates where the delta function lives, and the first index indicates on which segment we are measuring the influence. Okay, and each of these three bulk to boundary propagators can be written in terms of GR and GA, which are the bulk propagators, with some unknown constants in front of them, CIJR and CIJA. And our task here is to essentially find these unknown constants. And it turns out that this is actually a very simple thing to do, because we have 6 unknowns and we actually have 6 conditions to impose. 3 of those conditions come from imposing boundary conditions, and 3 more come by imposing the match conditions on the joints. Okay, so it's a very simple computation to get all these 6 constants, C, IJR, and CIJA. So this is when we have the delta function on segment on M1. Now we repeat the same with the delta function source on the boundary of M2. And in that case, we compute the bulk to boundary propagators delta ij. So the delta function source is on segment 2, and we measure the influence on all 3 segments. Okay, and with all those bulk to boundary propagators at hand, we just simply convolve with the sources to get the fields. So for example, if we want to compute psi1, so the field on segment 1, we have delta 1, 1, J1 plus delta 1, 2, J2. Now J1 and J2 are equal to each other and equal to JR. So we factor that out of the parentheses. And if we plug in the explicit constants that we found by doing the computation of on the previous slide, we get that this quantity here that you see in the parentheses looks something like this. So it only depends on GR. Okay. If we do the same calculation for psi2, we once again see that psi2 only depends on GR. And if we do the computation for psi-e, so the scalar field psi on the Euclidean segment, we see that that is trivial. So what has happened here is actually marvelous. So what happened, we put 2 delta functions here, one there, one here, but let's focus on this one at the moment. So the influence of that moved to the future and moved to the past. Through this join here, it went onto the Euclidean segment, all around the Euclidean segment. Through this joint here, it moved up on this Lorentzian segment, and it precisely canceled the influence of the other delta function source towards the past. Okay, in such a way that the inclusion of these 2 delta function sources has a causal response, so it only propagates in the future. This is an extremely nice result. Okay, so we see a causal response to the boundary sources that we have introduced. And in fact, this is precisely the Skenderis prescription. So instead of doing all the calculation that I just described on these three segments, you can just focus on one Lorentzian segment and impose ingoing boundary conditions at the horizon. Okay, this is precisely the Skenderis prescription for 2-point functions. Okay, remember psi1 is at order epsilon, so it controls the 2-point function. So this is the first boundary value problem that we had to solve. Now let's move on to the second boundary value problem, which is actually what we want to do. This is what will give us the 3-point function. Now, the sources are not in the boundary, they're in the bulk. And this is because if you remember, the sources come from this right-hand side. So they come from psi, and psi is a field that lives in the bulk. Okay. So now we have bulk sources. And we will essentially do a calculation very similar to what I showed on the previous slide. We'll start by considering a delta function source in the bulk of one of the two segments. Compute the now bulk-to-bulk propagators on all three segments. Then repeat the same calculation with a delta function in the bulk on the other Lorentzian segment. And then convolve with the sources in order to calculate the fields chi1, chi2, and chi-e. Okay, so let's start with a single delta function source on this segment here, in the bulk of this segment here. And now we want to compute the bulk-to-bulk propagators. Now, these bulk-to-bulk propagators essentially have the same form as before, and they depend on these coefficients Cijr andCija, just like before. And our task is to compute those constants. And we do that essentially in the same way as before by imposing boundary conditions and the gluing conditions at the joints. And when we put everything, so this is for delta function on one segment, we repeat the same thing for delta function in the bulk of the other segment. And then we have all the information that we need. So we can compute the fields chi1, chi2, and chi-e by convolving with the sources, which now are bulk sources, and they're given by psi1 square on segment 1 and psi2 square on segment 2. So chi1 will be delta 1, psi1 square plus delta 1, 2, psi2 square. But from the previous calculation we did, psi1 and psi2 are the same, so we can factor them out. And we have here, what's left is delta 1r. And if we plug in the precise expressions for these unknown constants, we get that delta 1r only depends on gr. So once again, we see exactly the same as what we saw before. We have a causal response to psi I. Okay, so information only propagates in the future. And psi Euclidean is trivially 0. So in the same way as before, actually this computation shows us that instead of doing this calculation on this piecewise geometry, we can simply consider just one Lorentzian segment and impose ingoing boundary conditions at the horizon. Okay, so the question that I posed earlier, whether the Skenderis prescription applies to higher point functions, the answer is yes. So at least at the level of 3-point functions, this is what we've proven here. Now, in terms of actually computing this 3-point function, we have now two options available to us. One is to go and explicitly compute these bulk integrals that you see here in order to compute the fields chi1, chi2, and chi3, or a bit simpler to just take advantage of this statement that we've proven here and do the calculation on a single Lorentzian segment imposing ingoing boundary conditions. And this is what I want to discuss in the next part of the talk. But let me pause and ask if there are any questions on this segment. Hopefully I haven't lost everyone.
I have a little question.
Yes.
You have this antisymmetric parts and this A and R parts. This indicates that you have a kind of hidden parity there in your problem, even or odd combination of your functions. When you're going through your construction, it seems that it's filtering out even or odd combinations. Have you been able to somehow to identify just the basic underlying structures which are hidden in these integrals and all these calculations? There should be some very simple relations. I'm wondering whether this is the case.
Sorry, let me clarify. What symmetric and undisymmetric?
No, concerning this symmetric combinations of the 2 points. You have this, for instance, for the sources, JR as symmetric and the antisymmetric ones, this JA.
Yeah.
And so everything in this integral representations and green functions and so on, it seems to boil down to simple combinatorics of this even odd combinations. And I'm wondering what's the basic underlying structure that is showing up here, that there should be some kind of this structure. Did you identify it? Could you identify it?
The short answer is no. So here we wanted to compute retarded 2-point functions and retarded 3-point functions. And this is precisely the reason we set JR to be non-zero and small, and JA to be equal to 0. Now, if you want to do something different, so for example, compute a different 3-point function or a different 2-point function, you need to consider something different. Okay. So in particular, I don't know, say we wanted to compute G. So at the level of 2-point functions, we computed GRA. Say we wanted to compute GAR. In that case, we wanted, instead of J1 and J2 to be equal to each other, we wanted them to be equal with opposite sign.
Yes, sure. Exactly.
Yeah. So yes, but in that case, this argument, I'm not sure how it will go through. If you have an idea, I'll be very happy to.
Okay, so we can discuss it afterwards. Okay.
Yes, yeah, that would be great. But no, it's not clear, and it's not even clear that if you want to do that calculation, whether the Son-Starnet's prescription of ingoing boundary conditions, whether that will apply. In principle, we can do the numerical calculation of this piecewise geometry, fine, but it's not clear whether this ingoing boundary conditions at the horizon, whether it will hold. It's more likely that it will not hold. So yeah, so that was a very long way of saying that we don't actually know what the underlying structure is.
Okay, thank you anyway.
Yeah.
I have also one question, one quick. Yeah. I think you said that of those 9 different combinations of R and A, of these 9 correlators, only 3 of them are free, correct? There
are only 3 that are independent.
Oh, independent. Okay.
Yes.
Then my question is, if we want to focus on Son-Starnet's formalism, are we able to calculate those 3 independent correlator just by considering this ingoing boundary condition or not?
Yes.
Are the 3 of them? Okay. Yes.
So this goes back to the previous question. So with the ingoing boundary condition, we can compute the retarded one, which is GRAA. So the R is in the first position and the other two are A and A. But it's not clear we can compute the other two. Usually people take the other two to be ARA, so they are in the middle position of the three, and GAAR, so R being the last of the three indices. It's not clear.
So do you confirm that the three independent correlators are causal correlators or not?
But that they should be, no?
I'm not sure.
Yeah.
I'm not sure.
Yeah, I don't know.
For 2-point functions, GRA is causal, and as you said,
Yeah.
We can reconstruct. Okay, so thanks.
So
Thanks.
yeah, GRAA, it is causal in the sense that we have, so on this figure here, we have the influence propagating in the future on this image. Now, as I was trying to explain for the previous question, so when we want to compute different correlators, then the sources that we need to put are not equal to each other. So here we had J1 and J2 being equal to each other with the same sign. So in order to compute other correlators, we need to consider potentially other choices, in particular J1 equal to minus J2. And in that case, it's not clear whether the influence will just be only in the future, which is essentially what the ingoing boundary conditions are.
Okay, great. Thanks.
Anything else? Okay, so let me move on to the next part of the talk. So here I'll show you some numerics that we did for the retarded 3-point function of the scalar field of interest. And in particular, as I said on the previous slide, we did this computation by taking advantage of the statement that we've proven, which is that to compute this quantity is sufficient to consider a single Lorentzian black hole space-time and impose ingoing boundary conditions on the horizon. And for convenience, we computed this quantity not in real space, but instead in momentum space. So we computed R3, which is a function of two momenta, P1 and P2. Okay. And just like what we did before, we have a perturbative expansion of our scalar field phi. At order epsilon, we have the scalar field psi, and at order epsilon square, we have the scalar field chi. And now, given that we have these two momenta, we can construct the following ansatz for these two fields. Remember, here we only have one single segment. So psi and chi, they do not carry an index here. It's not a piecewise geometry, it's just one single piece. But we can expand in terms of plane waves. So we can have a component of the scalar field that is proportional to a plane wave with momentum P1, and we call that psi1, and a plane wave and a field, a component psi2 that is associated with a momentum P2. And here I explicit the sources S1 and S2 for these two fields. Now, having this ansatz at order epsilon, this gives us the following ansatz for chi at order epsilon square. In particular, we have three terms: chi 1,1 that has momenta 2p1, chi 2,2 that has momenta 2p2, P2, and chi1,2 that has momenta P1 plus P2. Now, for the computation of the 3-point functions that we want, chi1,1 and chi2,2 will not contribute. So we can just forget about them and focus on chi1,2. Now, having these ansatz, we plug it into the equations of motion for psi and chi. And what we get is 3 differential equations for psi1, psi2, and chi1,2, which we need to solve subject to boundary conditions. Those boundary conditions are ingoing boundary conditions at the horizon, but we also need to impose boundary conditions in the UV. And these are precisely the conditions that we impose. Specifically, psi1 and psi2 have a source equal to 1. Remember, I pulled out the source S1 and S2 here. So this is fully generic. And they have they acquire a bev that I denote here by psi I delta. And chi1,2 does not have a source. As we said earlier, we want to just measure the response of this field, but it does acquire a vev, which I denote here by chi ij delta. Having this UV boundary expansion, then the retarded 2-point function is controlled by psi1 or by psi2. The two are equal to each other. And the retarded 3-point function is now related to the vev of the field chi1,2. So this is precisely the calculation we did. We solved for this field subject to these boundary conditions, and we extracted these vevs. Now, in order to do the calculation, we had to fix the number of dimensions. We considered 5-dimensional bulk. We consider scaling dimension that is 5/2, and we set the strength of the interaction term lambda to be equal to 1. And for simplicity, we did this computation at 0 spatial momenta. Okay. So this is the computation. Now, before I move on to show you the results that we got, let me briefly discuss what we expect to see. Okay. In particular, where do we expect to see singularities on this retarded 3-point function? In order to discuss that, is usually intuitive to consider contact diagrams. And remember, we are in lambda phi to the cube theory. So contact diagrams look a little bit, well, they look exactly like this, where the strength of the vertex is given by the strength of the interaction, namely lambda. We have ingoing momenta P1 and P2, and the outgoing momenta, simply by moment of conservation, is equal to P1 plus P2. So we expect to see singularities whenever one or more of these legs become equal to a quasi-normal mode. So in particular, when one of the 3 legs is equal to a quasi-normal mode, we expect to see a single pole. When 2 of them are equal to a quasi-normal mode, we expect to see a double pole. And if one is able to see a situation where all 3 legs correspond to a quasi-normal mode, then that would correspond to a triple pole. Okay, so this is what we expect. Now, a bit of notation. Here we have 2 parameters, P1 and P2. Both of them are complex, so we have a 4-parameter space to explore. So we had to be a bit clever as to how we presented these results. So we thought it would be more clear, instead of considering P1 and P2, to consider P and S. P is the total momentum, if you want, is the momentum of the outgoing leg, and S is the difference between the momenta of the 2 ingoing legs. And what we'll be doing, we will be fixing S to a specific value and then plot the retarded 3-point function on the complex P plane. Okay. And this is the result. So here I'm showing the real part of the retarded 3-point function for S being fixed to some generic value. And what we see is we see several poles. all of which are single poles. But as you can see, some of them are marked with circles and some of them are marked with crosses. And the reason is because their origin is different. So the circles correspond to the situation where the outgoing leg is a quasi-normal mode, and we refer to those as resonant quasi-normal modes. On the other hand, the crosses correspond to when one of the ingoing legs is a quasi-normal mode, and we'll call them driven quasi-normal modes. Okay, and then as you can imagine, when S is fine-tuned to very specific values, then some of these poles might collide to give higher order singularities. And this is precisely what we see on this plot here. So when S is equal to 0, then these two poles, these two crosses, collide with each other, and they give rise to a second order pole that corresponds to the two ingoing legs being quasi-normal modes. For a different, but again, fine-tuned value of S, we can get one of these crosses to collide with this circle that you see here, and we get a situation like this one, where one of the ingoing legs plus the outgoing leg are given by quasi-normal modes. The next question is whether we could see triple poles. And it turns out that in this specific theory that we focused on, the kinematics did not allow for such triple poles. But in principle, in other theories, such a thing might exist. And another, it is a result, is that we didn't see any additional poles, okay? At least at the level of 3-point functions, we didn't see any extra poles that weren't associated with quasi-normal modes. At order 4 and beyond, this might be the case, because in that case you have loops in your contact diagrams, so things might be different. But at the level of 3-point functions, we didn't see anything extra. Okay, and are there any questions at this point?
Yes, I have a question.
Yes.
I have a comment about this way of calling external leg.
Yes.
I think from what we know about CPT formalism or Schwinger-Keldysh contour, essentially A legs here will turn out to be some noise fields, correspond to some noise field or background fields. And that is R leg, which finally becomes a physical field like density. So in my understanding, R leg could be an incoming energy or momentum, and the two A legs should be some internal momentum. And I mean, when you say that two of these legs are driven quasi-normal modes, and one of them is resonant, it's a little bit, I think, strange to me, because I think finally these two legs should connect to some external R fields in order to complete a diagram. You know, at present, this diagram is not physical. It doesn't happen in any scattering process. Do you agree?
Well, I mean, just if you disagree with the terminology, that's fine. At least in my from my point of view, is when we are picking two momenta, P1 and P2, those are the input that you give to the numerical calculation, right?
Right.
So if I pick those to precisely sit at the quasi-normal modes, I'm essentially picking precise values for the ingoing momenta. That's why we call them driven. And in terms of the resonant quasi-normal mode, is because you have to sort of fine-tune your P1 and P2 such that the sum of the two actually corresponds to quasi-normal mode frequency. So in that case, the P1 and P2 resonate with each other to give you a quasi-normal mode. So they come together if you want. So this is the background why we gave those names. There was nothing
mathematically.
more
I totally understand. Yeah.
Yeah.
Okay. Thank you. Thank you.
Yeah. Okay. Now this was the main computation that we did. Now we were fortunate enough that, and I'm running very late, that we actually got some extra results for free. And the first result that we got for free is that we managed to get the retarded 3-point function TOO, so one stress tensor and two scalar operators, at least one component, TT component, for free by just considering the word identities. So the word identities in the RA basis look something like this. You take them into momentum space and you perturbatively expand these sources J, and they look something like this. And this second equation here, you can solve for the TT component of R3 TOO, and you get an expression that looks like this in terms of the retarded 2-point functions of the scalar operator. And this result can be extended to higher point functions. So for example, you can have TOOO, or at least the TT component of that. So that was the first thing we got for free. And the second thing we got for free is my answer to a question at the very beginning of the talk about the fluctuation dissipation theorem. So at the level of 2-point functions in momentum space, the fluctuation dissipation theorem looks something like this. It says that the symmetric 2-point function is given by the retarded and advanced one in this way, where n is the Bose-Einstein distribution. And we essentially showed, which we got it for free essentially, that this relation is manifest in the bulk to boundary propagators. So if we write the bulk to boundary propagators in the RA basis explicitly, so delta RA, RR, AA, and AR, we see that they take this form here when you explicitly specify the coefficients Cijr andCija. Okay, so we see that the retarded one only depends on GR. Delta AR only depends on GA. This makes sense because these two are related with time reversal. But the symmetric one, delta RR, explicitly takes the form of the fluctuation dissipation theorem. And this begs the question, can we understand the generalized fluctuation dissipation theorem for higher point functions in a similar way? That's an open question. It's an interesting question. And with this, let me summarize and conclude. So in this talk here, I computed the retarded thermal 3-point function, GRAA, for 3 scalar operators. And I computed essentially, I got it for free, the retarded 3-point function GRAA of the TT component of the stress tensor together with 2 scalar operators. We've also shown that real-time holography reduces to ingoing boundary conditions on a single sheet, extending the Son-Starnet's prescription to the nonlinear level. And we also saw that these retarded 3-point functions they have single poles and double poles. We didn't find any triple poles, but they have single poles and double poles precisely at the location of quasi-normal modes. So the universality that was seen by Son and Starnets that related black hole ring down and linear response actually extends to the nonlinear level, at least for 3-point functions. And with this, let me give a brief outlook. So we computed GRAA it's still pending to compute GARA and GAAR. And we want to do this calculation if we can in a simpler way that does not involve just doing numerics on this piecewise geometry. That can be done, but it's not an easy computation. We also want to understand better the generalized fluctuation dissipation theorem, possibly from the bulk perspective, as I showed a couple of slides ago. We also want to extend our results for 3-point functions of the stress tensor. So we want to compute G, T, 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 or in general, any conserved current. And last but not least, it will be great, and some of you might be know more than me about this. It will be good to understand the relationship between the Skenderis-van Rees approach of real-time holography and the Grossley-Glorioso U prescription, and not only to understand the how the two compare, but also compare results obtained in one prescription, like ours, with the results that were obtained in the other prescription, like, for example, some results that came out late last year by these people here. And with that, let me finish and apologize because I really overran. Thank you very much.
Thank you very much, Christiana, for a very clear and interesting talk and inspiring talk. Are there questions? Beyond, we already had a lot of questions, so it was totally fine that you went over a little bit because we included some questions, question time. So are there further questions? If I may start, I just wanted to ask about this very interesting result that you righteously correctly advertised as such, which is on slide 13, I think it was.
You were organized enough to keep the slide number.
Yeah, I think it's on slide 13. You have the
yes.
You derived the conclusion that after your calculation, according to Van Rees and Skenderis procedure, you get this cancellation in the backward time direction, and you get just a causal response from your source JR. And so I'm just trying to understand. So you mentioned that you proved this and so probably it's
no. Yeah. So let me be very explicit. I think this at the level of 2-point function was already known in the literature, or at least it was implied in the literature. Yeah. So yeah, but there was a paper by Van Rees that it didn't quite show it, but it implied it. Our contribution was to do this computation for the 3-point function.
Great. So I'm just trying to understand just a little more level of detail that I probably missed when you mentioned it. So should I be able to see from what's on the slide here that there is this cancellation in the backwards direction?
Yes, essentially the fact that only depends on GR precisely tells you that.
Okay? So that part I don't see. Is that because of the properties of how delta 11 and delta 12 are related to GR?
Yes. So remember, delta 11 and delta 12, we had them.
Okay.
We had them expressed in this way. So if you plug in the very specific expressions for the coefficient C, then you get cancellations, and the cancellations that you get are such that only GR appears.
Okay. So the values of these coefficients Cij is what I do not see.
Yes. Yes.
Right.
I didn't include them. I didn't think they would be too illuminating.
Okay, but you say that they are just such that this expression that you have on slide 13
Yes, yeah,
shows you a cancellation between anything
precisely.
not causal in the future direction. Okay, so relay. I mean, this is obviously you're saying that you're repeating this, and the same structure is happening for the 3-point function. I understand that. So that's why I'm asking another question. So if you were to shift the time, so in principle, there's a time translation invariance in the background here. So that is why you can shift the time always such that there's your correlator is between t1 and minus t1, right? That's what you have done here. Is that correct? Like for the 2-point functions?
I'm not sure what you mean.
Okay, let me say, I could choose to insert the operators or the delta functions in your calculation at some arbitrary t1 and an arbitrary t2, which is not minus t1, right?
Yes.
And I presume that you use time translation invariance of your underlying state to shift this correlator such that you have these two operator insertions at t1 and minus t1.
Well, essentially, that was my starting point, because I said J1 as a function of x to be equal to J2 as a function of x, right?
It gets interesting, I think, when you don't have an underlying time translation invariance.
Yeah.
So then the question is how to modify, how would that modify the story for the 2-point functions and I mean obviously then the 3-point functions. But thank you for explaining. I understand this part much better now. Thank you.
Excellent.
In the meantime, are there any other questions?
Question, Matthias. One last question from me. Can I ask?
Of course.
Okay. Thanks a lot for the very nice talk, Christiana. I guess I got your motivation for calculating this correlator. However, you may know that in the QCD community, that's a comment, not a question. In QCD community, and in particular for those who are searching for the QCD critical point, it is important to gain some knowledge about a 3-function, I mean density correlation function in a strongly coupled field theory, because it turns out that this correlation function is the most sensitive quantity to the existence of a critical point. So maybe if they know that you have calculated this quantity, they're waiting for you to see some GRRR correlation function. I think so. That's very important.
So this metric one. Okay.
3 I think, because it should correspond to some density correlator. Yeah.
Well, in principle, it will compute the we compute their GRAA. If we are able to compute the GARA and AAR, we can use the fluctuation dissipation theorem to get the GRRR.
Yeah, in the left side. Right.
Okay, that's
a comment.
Yeah. Could you maybe send me a reference about this?
Sure.
Yeah, that would be great.
I can send to you.
Thank you.
Thanks a lot. Thanks for the time.
Yeah, thank you for the comment, Navid. That might be very interesting. Like, I mean, in the sense of the HoloTube underlying theme of applied holography, then this might actually end up in some QCD talk slides and papers as a reference line, right? So that would be very nice. Any other questions? Well, if that is not the case, I don't see anything at the moment, then we will end the recording. And with that, thank Christiana again for your very nice talk. And thanks to everyone for the contributions to the discussion. And see you all next week.
Thank you very much.